So the deal is this. I'm going to talk a little bit about what's going on, work you through the steps. So this is, as you heard, an advanced persistent threat or a multi-stage attack. I'll talk a little bit about the attack, and then we'll switch to the attack itself. And Mislav, down at the front here, will show you some of the steps. So we've already implemented the attack, if you like, or up until almost the last stage already. So we'll show you some of the stages, and then we'll switch back to the slides and so on and so forth. OK, so I think if you were around earlier today, you heard me say this already. So we do smart grid security research. What is the smart grid? It's the future energy systems, basically, that have a larger number of renewable energy sources, such as photovoltaics, wind turbines, and so on. And they need distributed monitoring and control. And this new distributed monitoring control, which is implemented using ICT systems and SCADA systems, introduces new vulnerabilities and new threats. And some of those threats can result in physical implications to the power system, so power outages, shifts in voltage, power outage, voltage drops, frequency distortions, and so on. So there was an example of this type of attack last year in the Ukraine, where an attacker implemented a sort of an advanced persistent threat, implemented a number of stages that resulted in a substation tripping and a blackout for, I think it was 80,000 customers in this town in Ukraine. So this is the kind of attack that we're interested in. And here we're going to show you an attack to what could potentially be a set of photovoltaic inverters, but here we're going to just attack one. OK, so that's the setting. So if you were around for my colleague Florian Skopit's talk earlier, this diagram will look somewhat familiar. So what we have towards the bottom of the diagram here is an office network, which has a Windows 7 PC. We have a SCADA network, or an operational network, which has a data historian. So this is a Linux machine that is used to collect operational data from the grid, for example, for efficiency reasons. Then we have another machine, which is here is called an IEC 61850 client. So basically, that's essentially represents a distribution network management system, which is using a protocol, a telecontrol protocol called IEC 61850 to basically control the behavior of a photovoltaic inverter, or a set of them, which is deployed in the field. Over in the internet, we have our attacker, who has two pieces of infrastructure available to him. So he has a command and control server on the one hand, and on the other, he has a web server, which he'll use to engineer a social engineering attack, or use as part of a social engineering attack on some unsuspecting victim. OK, hopefully that's clear. So basically, the attack looks a little bit like this. So as I said, I'll walk through some of the steps. The first step is that the attacker sends a so-called phishing email to for example, a system administrator. Maybe before this, he's done some reconnaissance to see who the system administrators are, maybe called them up and asked them something about their systems. He sends them this email requesting them to update some software on some of their systems. The system administrator falls for this, so this is social engineering. They go to the website that's pointed to in this email. They download an infected program from the attacker's website. They run it because they think it's going to be upgrading their systems. This installs some malware on their machine, so this Windows 7 Office PC here. This malware then downloads further malicious software, a piece of software called a remote access Trojan, which basically allows the attacker in the internet to essentially control basically with the remote access Trojan installed, they have absolute control of their system. OK, so then that's the first two stages. So what we'll do is we'll switch to the live demo, and we'll show you the phishing email and the remote access Trojan and the kinds of things that we can do with it. So So this is essentially our target. So this is the web interface of the Fronius PV inverter that we've got. As you can see at the moment, it's operating at 100% of its active power, so that's the red bar there. In the end, we will hopefully, if everything goes to plan, we will switch that to 0, so we plan to switch that off. So if we look at the software side of things, so the phishing email. So this is the email that's sent to the system administrator, for example. So saying you must update your server, click on this link to download an executable. So the system administrator, in this case, downloads it, saves it. And runs it. And bam, they're infected. Okay? So at this point, then the attacker can, so at this point, the malware, so the remote access Trojan, the client side of the remote access Trojan is downloaded onto that Office PC. So the attacker has got a foothold in that network. And what we can see here is the server interface that the attacker has onto the infrastructure that the Office PC that they've just infected. So here you can see, for example, hopefully the CPU usage on the machine, the memory usage. You can see, for example, here that Mislav has brought up the directory structure on the infected PC, so we can take a look at that. He has some malware or some further files that he's interested in using later on in the attack. So he selects that and sends it to the machine. So at this stage, the attacker has a foothold in the infrastructure on that Office PC. All right, so we've got some steps to go to get to our PV inverter in the end. So if we switch back to the slides. OK, so from the Office PC, the attacker then basically scans the network for further machines to infect. So he might use a tool called Nmap to do this. And then he identifies a vulnerable machine in the SCADA network, our historian that I mentioned earlier. So this is a Linux machine that's maybe running a slightly older version or older distribution of Linux that's vulnerable to certain vulnerabilities. In particular, this historian has the shell shock vulnerability, which I think you heard about earlier. The attacker from the Office PC downloads a tool called Metasploit, which is used for penetration testing. And then they use that to exploit the shell shock vulnerability on the historian machine. So the attacker has gone from the Office PC, identified a vulnerable machine in the operational network, and exploited that using the shell shock vulnerability. Subsequently, the rat, again from the rat in the internet, we establish a connection on the historian, and then what we do is download a piece of software which is going to implement a so-called man-in-the-middle attack between our IEC 61850 client and the PV inverter. So this man-in-the-middle attack basically allows us to sniff the traffic or listen to the traffic that's going between the legitimate traffic, the normal traffic that's going between the 61850 client and the PV inverter, see that, change it, and then replay it as we see fit. I think I've said all that already. Yes. So this is the final setup. So basically what we have is the legitimate IEC 61850 client sending control messages to the control interface on the photovoltaic inverter, so changing the active power variables and so on. Over on the right-hand side, we have our attacker who sits in the middle in the network, listening to the traffic that's going there, installed on the historian in this case. They're talking this protocol IEC 61850. We have a Raspberry Pi in the middle, which is basically translating IEC 61850 messages to another protocol called Modbus, which then is actually controlling the behavior of the inverter. OK, so if we switch back to the video. So what we have here is, can we show once again maybe the web interface for the Fronius? Or No, OK. All right, so basically what we have here is we can send some commands, collect the status of the current status of the inverter. It's difficult to see at the back, but we can see that it's operating at 100% power. So now the system administrator, the grid operator from his distribution management system, this IEC 61850 client, sends a message to the PV inverter to reduce its active power output to 80%. So it might do this, for example, because of, why would they do this? I don't know. But they would do it anyway. This is picked up by our man-in-the-middle attack tool. So here we've collected it. So this is saying we want to change the voltage to 80%. So we've intercepted that. We set it to 0. So we've changed the active power setting for the photovoltaic inverter. And if we now return to the web interface for the Fronius device, you can see that the active power output is down to 0%. So we've effectively switched off the PV inverter. So we've had some physical implication from a cyber attack. And I think the inverters will have gone into standby mode. OK, so there we've shown this, where is it going? It's difficult to see. OK, so yeah, so in principle, we could do that for a large number of PV inverters. So from a network point, so for a whole installation, a whole low voltage grid line, or a medium voltage in the medium voltage distribution, and cause power perturbations, which could be problematic for clients and also the distribution system operator. So that's very nice, I think. It worked. So what can we do about that? So at AIT, we're working on solutions to sort of address this problem. So if you were around earlier, you may have heard me say some of this already. So we're really interested in smart grid-oriented risk assessment or risk management processes. So trying to understand these cyber-physical effects, developing tools and solutions to try and analyze them, what attacks are going to have the most impact, and so on. So we work closely with our colleagues in the energy department to do that, developing, for example, co-simulation tools where we can implement such attacks and then see how they play out in simulation or even with real hardware in the loop. We have a lot of work where we develop secure reference architectures for smart grids. So we have a national project called RASA architecture where we focus on, for example, the secondary substation and the customer side, where we, again, with our colleagues in the energy department, we define the ICT architecture and then analyze it in terms of risks and then come up with sort of architectural solutions like security enclaves, firewalling, anomaly detection systems, and so on. And then, of course, this is an advanced persistent threat. So it's going to be using things like zero-day vulnerabilities, social engineering, and so on. So this inevitably, or to some extent, the attack will be successful. So there's this notion that we have reactive security solutions. So basically, we want to try and detect. So our defensive measures have failed, or may have failed. So we want to detect that we've had an attack. So we develop anomaly detection solutions, in this case called ACID. So again, my colleague following Skopik talked about this, where we use machine learning techniques to understand the normal behavior of a system and then detect when it's behaving anomalously, which might indicate a threat. And then if we detect a threat, we might want to share that information with people or organizations of a similar type to us, so with other DSOs and so on, and in operational context. So we have this tool called CESAR, or a solution called CESAR, where we can share information, which then hopefully can be actionable and help to reduce the overall impact of the attack that we've just shown. OK, so that's the presentation. Just to quickly acknowledge, so this work was done in one of our European projects. And it was a team effort to get that together. So we worked closely with our colleagues at RSA, Queen's University Belfast, and also at AIT. There was a team behind it. That's it from me. Thanks very much for your attention. And if you want to know more, we'll be here at the stand during the coffee break.
Thank you, Mr. Smith.